Hello and welcome to this course. I'm Dr. Sriram Kumar. In last class, we had discussion about the properties of carbon nanotubes, and we have understood the application of carbon nanotubes in electronics applications, composite material applications, energy storage, field emissions, optoelectronics, biomedical and environmental applications, and we understood the key properties of carbon nanotubes you can use for specific field of application of carbon nanotubes there. Now let's understand synthesis of carbon nanotube. So in this class, we are going to learn three different methods of synthesis of carbon nanotubes. One is arc discharge method, second is laser ablation technique, and third is chemical vapor deposition technique. So our main goal is to develop a technique so that we can have this quality control over the synthesis of carbon nanotube. And the second important goal is to achieve the high yield of that carbon nanotube. So based on your application of carbon nanotubes, you can choose either arc discharge methods, laser ablation method, or maybe the chemical vapor deposition technique. So now let's first learn about arc discharge method. So in arc discharge method, there's 4 to 5 important steps. So we are going to learn one by one in arc discharge method. So first important method setup in the arc discharge method is the electrode setup. How we are going to set up electrode is very important things here. So in this method, we can use two high pure graphite rod. So here's one accesses the anode and the second accesses the cathode. So we are going to use two graphite rod. That is, one is anode and the second is the cathode. For example, in this diagram, we have here, so this is the anode material and this is the cathode material, that is the negative charge here. So now we can also modify that electrode based on our type of the CNT material. For example, if you want to develop single wall CNT, so in this case, we need to use catalyst. So we need to use the catalyst, maybe the iron, cobalt, or nickel-based catalyst on anode material. So we should use this catalyst at anode material. Okay. For example, so this is anode. So for the single wall CNT, we need to use this catalyst material on the tip of that anode. And for this multi-wall CNT, we don't need to use any kind of this catalyst. For example, here's this anode. So if you want to develop the multi-wall CNT here, so we just use the blank or the plain anode material, that is the graphite electrode. And if you want to understand what is the condition in that closed chamber, so in this arc discharge method, we need to use inert gas. Normally, we use either helium or maybe the argon inert gas in that arc discharge method. So here the purpose of using the inert gas is that stabilizes the plasma formation in that process, and that stable plasma gives uniform quality of this material. So first, important aspect of the RF discharge method is the how you set up electrode. So in this method, we can use two electrodes. One is anode and the second is cathode. Both are made of the graphite material. And for the single wall CNT, we need to use catalyst. And for the multiple CNT, we can use the plain electrode. Okay. Now we have the second important aspect and step is the how we can generate plasma inside our discharge chamber. So here we should use a very high current between anode and its cathode. For example, if you want to understand here, so we have this is the anode, this is the cathode, there is the positive charge and this negative charge, and we apply here is the very high current in the range of 30 to 100 ampere. So what happens because of the very high temperature current at the anode and the cathode, there is the generation of the plasma, and the temperature of that plasma might increase up to the 4000 degrees Celsius. So whenever we apply very high current between anode and cathode, we get this plasma, and the temperature of that plasma here is close to the 4000 degrees Celsius. Now let's understand that what plasma does inside the chamber here. So whenever we get with very high plasma, so because of the that plasma, so at high temperature, so there is kind of the carbon vaporization process happens, and because of that vaporization happens from anode, we get the plasma here, and that plasma consists of carbon atoms, ions, and the small clusters. So in the second step, what we understood is that we need to apply very high current between anode and cathode, and that is 30 to 100 ampere. So when we apply this high current, we get kind of the temperature that is 4000 degrees Celsius. So because of that very high temperature, there is the vaporization happens from anode, and that vaporization happens from the anode from this surface, and there is formed of this here the kind of the plasma. So we get the plasma of these carbon atoms and so maybe the small clusters. Okay, now let's understand once we get the plasma, what is happening there. So now we need to understand carbon nanotube nucleation and the growth process. So once we get here the plasma here, and we have here the cathode. So here that's vaporized carbon atoms get deposited on the cathode material. So there is kind of the condensation process happens at this cathode surface, and once we get the enough concentration of this carbon on this cathode material, so there is kind of the nucleation process starts. We already understood how the nucleation process starts with the concentration. So if we have the concentration, so we already understood that if we have this kind of this graph here, so we have this kind of this graph here. So we have, so if we get the concentration in this particular range, then so this is kind of the nucleation process, and this one is kind of this. So this range is the growth steps of the nanomaterial, and we have this growth mechanism here. So once we get the nucleation at this cathode material, so thereafter we have this growth of kind of this CNT on the surface. So first what happens, so that contains carbon atom that rearrange to form this curved graphene sheet there, and if there's the curved graphene and then it's rolled up to form the carbon tube. So here, based on the kind of the catalyst we use there, so there are different kind of rolling, maybe the armchair, zigzag, or maybe the carols closing, and this one that we'll get this conducting metallic or maybe semi-metallic carbon nanotubes here. So now let's understand what is the role of the catalyst here. So here the catalyst helps in the seed of this growth of this carbon nanotube, and that also control what would be the diameter of the CNT and the wall thickness. So here that wall thickness depends on the single wall CNT or maybe the multi-wall CNT. And at the same time, it also control over the crystallinity of the carbon nanotubes. So here the catalyst is very, very important. So if you want to make either amorphous, maybe the crystalline CNT. So here if we use a catalyst, so for that we need to have the crystalline CNT for the more effective applications of these materials. And at the fourth step, what we have here is once we will have here this carbon nanotube is there at cathode, and we can collect that material from that cathode. But the problem is that that material is not 100% CNT. So we maybe get the kind of the compositions of CNT, fluorine, maybe the amorphous carbon, and sometimes the graphitic particle as well. So we need to collect the material deposited on the cathode, but that has the composition. We need to purify. So for the purification, what we do, we can use two kind of the purification. One is the acid treatment. So by the acid treatment, we remove the metallic contaminations, catalyst remove metallic particle. For example, if you use iron, cobalt, or maybe nickel as a catalyst there, so that might be present in that CNT. So if we just use maybe S2SO4, or maybe the nitric acid and mild conditions. So what happens to that? So this acid dissolve that metallic particle, and you can remove that metallic particle. Or maybe we can use the physical method, maybe the centrifugation technique. So in the centrifugation techniques, in this metallic particle has higher density as compared to the carbon material. So we can remove that metallic contaminant from the CNT. So this is about the carbon nanotube synthesis using arc discharge method, and this is a summary of the flow chart of the CNT synthesis. So in the first step, we should use here in the first method step is that we need to use two graphite rod. One is the anode and the second is the cathode. And if you want to develop multi-wall CNT, so we just use the plain graphite rod. And if you want to use single wall CNT, so for that we need to use the catalyst, maybe iron, cobalt, or nickel catalyst. And the second step is about the reaction chamber condition. So in this case, we should use the inert gas, maybe use the helium or maybe the argon. So this one is used to stabilize plasma formation inside this chamber. And the third step is about to apply the very high current between anode and the cathode. So when we apply very high current, there is kind of the arc formation there. And because of the very arc formation and temperature is close to 4,000 degrees Celsius, there is the vaporization of carbon from the anode happens. And that vaporized carbon atoms from anodes gets condensed on the cathode material. So cathode surface, and once we get this kind of this critical concentration, then there is a nucleation process starts, and once the nucleation process achieved, then there is the growth of the CNT start. So here the types of the CNT depends on the kind of the catalyst we use there. And once we collect that carbon materials from cathode, with that maybe have this fluorine, CNT, graphene, maybe the graphite powder. We need to purify the CNT and to collect and purify it. So this is all about this arc discharge method. Now let's understand what are the factors that can affect the arc discharge method. So first and foremost important aspect is the arc current and the voltage. So if you want to develop unit and quality control of CNT synthesis, then we need to control over the intensity of electrical arc. At the same time, they should be stable in nature. And the second is the rate of evaporation from anode, so that evaporation happens from anode to cathode, right? So evaporation starts from anode, and that is condensed at cathode material, and that also affects this arc current and voltage on the yield and the quality of the CNT. So here the arc current and the voltage is very important here. So this arc current we can use the 3200 ampere, and that maybe if you apply the voltage there, we should use a very high voltage. And the second most important factor is the electrode composition and the catalyst. So for the multi-volt CNT, we just use plain graphite rod, and if you use the develop the single volt CNT, for that we need to use the catalyst there, maybe that iron, cobalt, maybe the nickel based catalyst to control the diameter of single volt CNT. And third important aspect is the inert gas pressure and the type. So here the inert gas pressures helps in the stabilization of that arc there, and that also helps in the controlling the cooling rate of the vaporization carbon species, and that also affects the nucleation density and overall the morphology of the nanotubes. And the four important factors is the distance between anode. So suppose one is the anode and second is the cathode. So here the distance between anode and the cathode is very critical, because here the arc formation between these two electrodes depends on the space between these two electrodes. So here, so we need to find control over the electrode separations, and that will help us to reproduce the synthesis of carbon nanotube. So these are those important factors to synthesize carbon nanotubes using arc discharge method. Now let's understand what are the advantages. First advantage is that from this method we will have high quality CNT. Second is the simplicity in setup. So there is no rocket science in the setup of the arc discharge method. You just need to have the closed chamber in which you have the screw electrode, another cathode that is finely tuned the gap, and you just need to apply the very high current with the potential high voltage between these two electrodes. So this is very simple setup. And the third is the disturbance. So yes, so here and third important thing is that initially the scientists were developing fluorine from this graphite material, but sometime one scientist observed that there is some amount of CNTs also there with the fluorine. So later on, they optimized the parameters of the synthesis of that CNT. So this is the first 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 kind of the techniques to develop carbon nanotubes using arc discharge method. But here some limitations are also there. One limitation is the low production yield, and the second is the purity issue here, because in this methods you may have this compositions, you have this CNT, you have the fluorine, you have the graphite material. So there is another challenge to purify the material. So that is the purity issue is there, and the second and third is the scalability. So this methods cannot be used for scalable and in shape like fabrication of the CNT. And the fourth important limitation is about the process control here. So here the process control means we need to control over the distance between anode and the cathode. That is very important in uses. And once we have the distance, then we need to have the stabilized arc formation. So we have the arc formation, and that should be the stable in nature. So these are the very important things we need to control over. Otherwise, we have the kind of the mixture of the different materials, carbon materials. Okay. So this is all about this arc discharge method. Now let's understand the synthesis of carbon nanotubes using laser ablation method. In a laser ablation technique, we have 4 to 5 important steps. As I already explained, the different physical method of nanomaterial synthesis. So in laser ablation method, you have target material, and you need to put very high power of laser on that target material. So because of that high power laser, so there is the vaporization happens from that target material, and that there is formation of plasma, and that it gets deposited on the collector, on the wall of the container, and then we can collect this nanomaterial from that surface. Now let's understand what is specific design for CNT synthesis. So first is the target preparation. So target preparation is the material we want to vaporize, and from that material we need to synthesize carbon nanotube. So in the target, we need to have the composition. So we need to use here the graphite powder, and we need to mix with the kind of this catalyst here, iron, cobalt, or maybe nickel kind of this catalyst metal there. So we use the graphite powder and then mix with this catalyst, and then we need to sinter that material so that we will get kind of the here dense target materials that can sustain and absorb the high power laser. So, and the second, first about the target preparation, and the second is the reactor setup. So in the reactor setup, what we'll do is here, so the first is the chamber environment. So in this conditions, we need to use the inert gas conditions. Maybe we use the helium or maybe the argon, and the temperature inside of this reactor should be close to the 1200 degrees Celsius. So first we understood about the target preparation. So in target preparation, we use the graphite powder, and then with this catalyst, and then we need to compress and sinter to form the dense target. And the second is the reactor setup. So in this reactor setup and furnace, we need to maintain kind of the inert atmosphere, and the temperature of that furnace should be closer to 1200 degrees Celsius. And the third important step is the laser ablation. So once you have target, once you have the conditions of the chamber, then we need to use a very uh, laser ablation technique. So in this laser ablation, we need to use very high powered laser. And so for in particular application, uh, so this kind of the laser is normally used. So NDYAZ means laser. ND is the neodymium, and here we use the YAZ, Y for the tritium, and A for aluminum, and the G for the granite. So this is the formula of the NDYAZ kind of the solid state laser. Maybe we can also use alternative laser is the CO2 laser. So we can use the either of these lasers with the high power pulse laser, and we need to optimize the critical parameter of the laser, including the pulse duration, energy densities, repetition rate, and the wavelength. So whenever we use the laser to vaporize the target materials, we need to optimize parameters, and these are the important parameters to optimize. And so we have here this target. And when we put the high power laser there, so what happens? So there's evaporations happens, and there's formation of the plasma, and that plasma and this gets deposited on that collector. So here the material evaporations happens, the vaporization of the carbon and the catalyst mixtures, because the target may have this only graphite powder, maybe the mixed with this catalyst, and the generation of the hot plasma, that mix of this carbon atoms, molecular clusters, and the catalytic metals particles. So once we put high power laser, there's evaporations, and that evaporation leads to the formation of the plasma, and the plasma has the main composition things, and this gets deposited, condensed on this collector. So now let's understand what is the nucleation and the growth of this carbon nanotube. So that is the condensation happens. So that once the condensation happens and that collector, then after we will get the nucleations. So that nucleation happens once there is the critical concentration achieved on that collector substrate. And here that nucleation and the structure of that material, that is controlled by the catalyst we use in that target material. So here carbon atoms and the catalyst both are there. So here that catalyst particles control over the structure, maybe the single wall or maybe the multiple CNT. And here we the position on the polar wall of the reactor tubes on the surface, and so here we need to use here the low temperature so that plasma gets condensed over the cooler surface, and the formation of the kind of the CNT. Okay, so once we get the CNT on the collector, then we can just harvest that material, then collect that material from that surface. So here the harvesting is the collections, and then after we need to purify that CNT. So once we need to purify to make the high purity, but sometimes we get the impurities in terms of the amorphous carbon or with the residual catalyst particles. So in this case, we need to use the acid treatment or maybe the thermal oxidations to remove some catalyst particles from the CNT. Okay, so in the laser ablation method, what we have, so first and foremost is we need to talk about the laser. What kind of the laser parameter we should use? So first is the target synthesis. So in this target, we need to use this graphite material, and that is mixed with this catalytic metal. Okay, and the second is about this kind of the reaction chamber. What kind of the conditions we use? So we should use the inert atmosphere, and we need to preheat that chamber close to this 1200 degrees Celsius before putting the high powered laser. So once we have this condition ready there, then so here the temperature is close to 1200 degrees Celsius here, and the third is about here we need to use the high powered laser. So here in laser in form of we need to use the neodymium, tritium, aluminum, granite, or maybe the CO2 laser. And in presence of this high powered laser, so there is the vaporization happens from the surface. There is a formation of this hot plasma, and that gets uh, condensed on this collector, and there's nucleation process happens, and the growth process happens. And once we get the CNT, then we can collect and the process to purify that CNT. So this is all about the laser ablation method. Now let's understand what are the factors that can affect overall the quality of the CNT in the laser ablation method. The first important parameter is the laser characteristics. So if you want to reproduce quality of the CNT, then we need to use here to optimize the pulse duration and the energy density of laser. And the second important about is the repetition rate, and that controls the ablation efficiency and influence the yield of the CNT. So here there is very important thing is to optimize the laser parameters in terms of the pulse duration, energy density, repetition rate, and the second is about the catalyst composition. So we need to use the composition and because the composition in terms of the mixing with the catalyst, first there's dimension and quality of the CNT there, and the third is the reactor's atmosphere and the temperature here. So we need to use the inert atmosphere and the very high temperature so that we have the uniform formation of the plasma in uh, in in the chamber. And we have here the fourth important parameter is the target quality. So here target quality means if you use the refined powder and mix with this catalyst. So once we sintered to make the kind of solid material, so that should be uniform in nature, so that we get the uniform plasma composition of plasma, so that we get the uniform quality, the quality control over CNT formation. And we have the advantages of the laser ablation method, and these advantages are in terms of the high purity and quality, because the laser ablation method gives the high crystalline line CNT with the fewer defects. And second important advantage is that we can control the environment here, so that environment controls in the synthesis conditions, and because of that we get the narrow distribution in diameter and the wall number, so we'll get the high quality of the CNT. And we have and this material is especially good for the single wall CNT synthesis. And the third advantages are the reproducibility. So this method is reproducible for the research application. However, there are some limitations in terms of cost and scalability. Since we are using here the laser, so laser always comes with a very high cost and maintenance. So that is the cost very so high power laser and control atmosphere reactor comes with the high cost, and the second is the scalability for the mass production, and yield in terms of that it gives a very high purity in pure CNT, but the problem is that the yield of the CNT is lower than its chemical vapor deposition stability methods. And the third important limitation is the complexity of the laser setting, because there are the many parameters of the laser in terms of the wavelength, power, pulse, and the durations. So optimizing the laser parameters are very critical things here. So these are the important limitation of laser ablation technique. Okay. So in this class, we understood two important methods of CNT synthesis. One is arc discharge method, and the second is laser ablation technique. In next class, we are going to learn chemical vapor deposition technique to synthesize carbon nanotubes. So see you in the next class.